You know the feeling, right? That pile of papers, articles, maybe research, your own notes. It's just sitting there,
Hmm.
full of potential, yeah. Packed with vital info, maybe even some game-changing insights, but actually turning that stack into knowledge, well, it feels overwhelming sometimes.
Absolutely. It's like having a treasure map, but you're not quite sure where to start digging.
Exactly.
So our mission here with the deep dive is kind of to be your guide. We take that stack, we dig deep, pull out the crucial nuggets, find the surprising
Look the
facts.
dots.
Yeah, help you connect the dots so you can be genuinely well-informed without getting totally lost in the weeds.
And today, we're diving into a really foundational stack.
Hmm.
It's all about the principles of environmental health and engineering.
Right.
Our sources, they cover a huge territory.
Yeah.
I mean, everything from the water coming out of your tap, the trash you take out,
Right.
to the air you breathe, even the noise around you every day. It's these interconnected systems working constantly, often invisibly.
Right, invisibly. To protect public health and the environment. It's the science, the regulations behind so much stuff we just, well, take for granted.
Okay, so let's roll up our sleeves then. We're going to unpack these sources, pull out what's most important, understand why it matters for our health, our communities.
Give you some solid ground in what can be a pretty complex field.
Okay, let's unpack this stack. So let's start with maybe the most direct connection. What makes us sick? Our sources really lay out how environmental factors contribute to disease, starting with the basic idea of a communicable disease.
Right. Think of it as an illness caused by a specific infectious agent. You
Yeah.
know, bacteria, viruses, protozoa, worms, even prions, the sources mention.
Wow, okay.
And it gets transmitted from some source. Could be a person, an animal, maybe the environment itself, like soil or water, to someone who's susceptible.
And the sources highlight some key ways these things spread, right? Like
Yeah.
the air,
Respiratory, yeah.
waterborne, foodborne.
Insect-borne, too. And zoonoses, that's diseases from animals.
Okay, examples.
Well, the sources mention things like poliomyelitis, often linked historically to bowel discharges getting into sewage, then food or water,
Okay.
or think plague, epidemic typhus spread by insects, rabies from animal bites, that's a classic zoonosis, and mosquito-borne diseases like dengue, encephalitis, constant challenges.
But it's not just about catching a bug, is it? I mean, the sources really emphasize how the environment hits non-infectious diseases too.
Oh, absolutely. This is where you get into things like, well, invisible poisons, environmental contaminants linked to long-term health issues.
Like air pollution.
Exactly. The sources link it to immediate stuff like irritation, lungs, nose, throat, eyes, but also serious long-term effects. Carbon monoxide, COO, can worsen cardiovascular problems.
All right.
Ozone, it's not just smog. The sources say it actually ages and damages lung tissue over time.
Wow.
And then specific hazardous air pollutants, they mention vinyl chloride, lead, benzene, asbestos, mercury.
And they link those to really serious things.
Yeah, things like lung or liver cancer from vinyl chloride or brain damage from lead, especially in children. That link between lead and retardation or brain damage is something the sources really underscore.
That's chilling. And it ties into other non-infectious problems too.
Definitely. Cardiovascular disease, for instance. The sources connect it not just to diet fats, cholesterol, sodium, but also environmental factors like sensitivity to carbon monoxide and things like obesity and alcohol linked to hypertension.
Heavy metals seem to come up a lot too.
They do. Mercury, for example. Found in fish, the sources cite levels like 1.3 parts per million, sometimes higher, but also in air, water, soil.
And lead again?
Lead again, especially from corrosive water leaching it out of old lead pipes or solder joints.
In older homes, yeah.
And other metals too, cadmium, zinc from soft water on galvanized iron pipes, antimony, lead, cadmium, tin from, say, old pewter containers, or even pottery glazes if they weren't fired properly. Shows how contaminants can be sort of hidden in everyday things.
Thinking about all these risks, it feels a bit daunting. But the sources also give some historical perspective, right? There's a table in there.
Ah, yes, the life expectancy jump. It's pretty dramatic. Between 1900 and 1990 in the U.S., life expectancy at birth shot up by, 26.2 years.
That's huge.
It really is. And that incredible leap, it's not just random. It's powerful proof of the public health advancements we're talking about, many rooted right here in environmental health and engineering, shows the real impact.
So how is that impact achieved?
Huh.
The sources talk about two main kinds of prevention, primary and secondary.
Exactly. Primary prevention is the ideal, right? Stop the disease before it even starts.
Like vaccines.
Immunization is a huge part of it, yeah. The sources mention different types, active versus passive immunity. using things called immunobiologics like IG or antitoxins to give your body protection.
Okay.
But it's also really fundamental environmental controls, making sure there's enough safe water, basic sanitation, public education about hygiene, good nutrition, maternal and child care, all primary prevention.
And secondary prevention.
That's about catching things early if primary fails. So disease surveillance systems to spot outbreaks quickly, screening programs, continuously monitoring the environment for hazards.
Like testing water supplies.
Right, and treating them. Fluoridation for dental health is mentioned as an example of treating a public water supply for secondary prevention benefits.
And if an outbreak does happen.
Then there's a structured investigation process. The sources actually show examples of forms, like for a foodborne outbreak investigation. They look at all the environmental factors, water, food handling, housing, sewage, insects. It's systematic, trying to find the source and stop it happening again.
Okay, so contaminants, disease agents, direct health impacts. But maybe the most fundamental environmental protection system is just water. Let's dive into what the sources say about water supply, quality, treatment.
Yeah, it all begins with the water cycle. Rain, runoff, water soaking into the ground, groundwater flow, plants releasing water, evaporation.
The classic diagram from school.
Pretty much. But it gets complex fast. The sources introduce how groundwater actually flows, even mentioning Darcy's Law.
Darcy's Law.
Yeah.
Okay, what's the gist of that without getting too technical?
Think of it like the rule book for how fast water seeps through soil or rock underground. It basically says the speed depends on the material, how permeable it is, and the slope of the water table, sort of the hill, the water's flowing down, and the area it's moving through.
Why does that matter?
It's crucial for figuring out where to put wells safely, how far away from potential pollution sources they need to be, and how quickly contamination might travel underground towards them. Understanding that flow speed is key.
Got it. So water sources, surface water like streams and lakes, and groundwater from wells and springs.
Right, and the sources are clear. Surface water, unless it's thoroughly treated, you have to consider it potentially unsafe. Needs investigation of the whole watershed area it drains from.
Which leads straight into water quality standards. Heavy reliance on federal regulations here, like the Safe Drinking Water Act.
Yep. You've got primary standards. Those are the ones directly related to health. Microbiological contaminants are huge here. The goal is zero coliform bacteria. Things like E. coli, Klebsiella are used as indicators that fecal contamination might be present.
Zero tolerance for those.
Pretty much. Turbidity, or cloudiness, is also a primary standard, not just because cloudy water looks bad.
But because things can hide in it.
Exactly. Bacteria and viruses can be shielded from disinfectants by the particles causing the turbidity, so low turbidity is essential for effective disinfection.
Primary standards also cover chemicals, right? Inorganic, organic.
Long lists. For synthetic organic compounds, think pesticides, solvents, industrial chemicals like dioxin. The sources talk about MCLs and MCLGs.
Okay, break this down.
MCL is the maximum contaminant level. That's the legally enforceable limit allowed in drinking water. MCLG is the maximum contaminant level goal. That's the level below which there's no known or expected health risk. It's the target.
And for carcinogens.
For probable human carcinogens, the MCLG is set at 0. That's the ideal no exposure. The actual MCL might have to be higher because getting to absolute 0 isn't always technically or economically feasible, but the goal is 0 risk.
Makes sense. Radioactivity standards are in there too.
Yep, radium, beta photon emitters, uranium. Then you have secondary standards. These are more about welfare things affecting taste, odor, color, staining, corrosion.
Like pH?
pH, yeah.
Yeah.
Chloride, which affects taste and corrosion. Copper paste and staining, like blue-green stains on sinks. Foaming agents. Sulfate, which can have a laxative effect and affect taste. And total dissolved solids, TDS.
TS, all the stuff dissolved in the water.
Basically, yeah. High TDS affects taste. It's also related to water hardness, and some sources mention potential links between very hard or very soft water and cardiovascular disease, though that's complex. High TDS can also indicate potential for corrosion or scaling. The sources even classify water by TDS, fresh, slightly saline, and so on.
And specific contaminants get highlighted again here. Lead.
Always lead. The EPA action level is triggered if more than 10% of homes tested show lead above 15 micrograms per liter at the tap. Then action is required by the water system, usually related to corrosion control or lead service line replacement. Sources are plumbing materials, as we said.
PCBs.
Polychlorinated biphenyls. They're seen as indicators of past industrial waste, maybe from old electrical transformers or capacitors. Big concern because they persist in the environment, build up in the food chain, and are linked to cancer risk. Their manufacture was banned years ago under TSCA, the Toxic Substances Control Act.
What about sodium?
Linked to heart and kidney disease concerns for people on restricted diets. Sources can be natural, but also water softeners that swap calcium for sodium, road salt runoff, even some water treatment chemicals. Bottled water sodium levels vary too.
And hardness. Scale buildup in pipes and heaters.
That's mostly calcium and magnesium ions. Causes scaling, makes soap less effective. The sources mention common softening methods like lime soda ash treatment at a plant or ion exchange using zeolite filters like in home water softeners.
Okay, so getting that raw water, whether from a river or a well, up to these standards, that involves treatment.
Right. The sources describe conventional treatment pretty well. It usually starts with coagulation.
Adding chemicals.
Yeah, chemicals like alum or copperous iron sulfate are added. They cause tiny suspended particles, the stuff making water cloudy, to clump together into larger, heavier particles called flock.
Okay, so they clump up, then what?
Then sedimentation. The water flows slowly through large basins, and that heavier flock settles out by gravity.
Makes sense.
After that comes filtration, usually through layers of sand and gravel, sometimes anthracite coal. This removes even finer suspended particles, including many microbes.
And the final step?
Disinfection, absolutely critical for killing any remaining harmful pathogens. Chlorine is the workhorse here.
How does chlorine work exactly? The sources go into some detail.
They do. The real killing power comes from a specific form called a hypochlorous acid, which forms when chlorine dissolves in water. Its effectiveness, its germicidal efficiency, depends heavily on the water's pH. It works much better at lower pH.
Okay.
Also crucial are contact time, how long the chlorine is in the water, and the water temperature. Warmer water, faster disinfection. But, as we said, turbidity interferes. It can shield microbes.
So clear water is key for chlorine to work well.
Absolutely. And the sources note that hypochlorous acid is much more potent than other forms of chlorine that might be present, like the hypochlorite ion, which dominates at higher pH, or chloramines, formed if ammonia is present.
What about removing specific problems like, say, iron?
Iron and manganese. They cause those reddish-brown or black stains, metallic taste, and can actually encourage the growth of certain nuisance bacteria in pipes, like crenothrix or leptothrix.
How do you get rid of them?
Several ways mentioned. Aeration exposing water to air can oxidize the iron and make it precipitate out. Chlorination also oxidizes it. Then filtration removes the solid particles. Sometimes lime treatment or special zeolite filters are used. Polyphosphates can sometimes be added to keep low levels of iron dissolved, preventing staining, but that doesn't actually remove it.
And tastes and odors, that swampy smell sometimes.
Often caused by algae or other microorganisms growing in reservoirs or decaying organic matter. Sometimes industrial pollution or even salt intrusion. The main tool mentioned for removing tastes and odors is activated carbon.
Like in Brita filter.
Kind of, yeah, but on a much larger scale. It can be added as a powder during treatment, paquet, or used in large filter beds made of granular activated carbon, GAC. Carbon is amazing at absorbing those odor-causing organic compounds.
And for really salty water, desalination.
Right. For reducing very high TDS, like in seawater or brackish water, the sources mention advanced processes like distillation, boiling and condensing, reverse osmosis, forcing water through a membrane under pressure, or electrodialysis, using membranes and electric current. Expensive, but necessary in some places.
Thinking about the whole system, design is crucial too, right?
Yeah.
How much water does a town need?
Yeah, engineers have to estimate peak demand. That's usually the highest usage hour of the highest usage day of the year. Think hot summer evening when everyone's watering lawns and showering. It varies a lot by the type of community.
And they use average usage rates.
Gallons per capita per day, yeah. That helps figure out the overall volume needed. And increasingly, the sources highlight water conservation fixtures, low-flow toilets, shower heads, faucets. They mention states adopting regulations with specific limits, like gallons per flush or gallons per minute. Saves water, reduces wastewater flow too.
Good point. And inside buildings, plumbing details matter.
Hugely important. Backflow prevention is critical devices that stop contaminated water from, say, a hose submerged in a puddle, from being sucked back into the clean drinking water pipes if pressure drops.
Yeah. Don't want that.
Definitely not. And indirect waste piping for things like refrigerator drains or water softener discharges, ensuring there's an air gap so sewage can't back up into them. Plus, as we discussed, the materials themselves avoiding lead solder, being aware of leaching from old pipes.
Right. And wells. Anything specific there?
The sources distinguish between shallow dug wells, which are more easily contaminated from the surface, and deeper drilled wells. Proper construction of a drilled well is key. Casing, grouting to seal it off from surface water infiltration.
And location matters.
Immensely.
No.
The sources talk about recommended minimum distances from septic systems, barns, etc., but stress that a proper sanitary survey considering local geology is essential. Wellhead protection regulations aim to protect the area immediately around the wellhead and sometimes a larger zone contributing water to the well.
How do you get the water out? Pumps.
Gotta have pumps for most systems. The sources list different types: displacement pumps, like reciprocating or rotary pumps, and centrifugal pumps, including the submersible type commonly used in wells.
Do they mention limits? Like how high water can be lifted?
Yeah, they discuss atmospheric pressure and practical suction lift, how high a pump at the surface can theoretically pull water up. There's a table showing it decreases with altitude. Of course, submersible pumps push water up from below, avoiding that limitation. Pump controls, pressure switches, float controls, and efficiency are also mentioned. It's a whole engineered system, top to bottom.
Okay, so water comes in, gets used, then it goes out as wastewater. Let's talk about the waste we create, both liquid and solid. The sources cover wastewater and solid waste management pretty thoroughly.
They do. And one surprising thing from the wastewater section is just how many people still rely on individual on-site systems.
Like septic tanks.
Septic tanks, cesspools. The sources cite stats suggesting millions of U.S. households use them, discharging, get this, billions of gallons of sewage treated or partially treated into the ground every single day.
Billions. Wow, that's a huge volume going into the groundwater system, potentially.
It is, which is why proper design and maintenance are so critical. For septic systems, the sources hammer on the importance of soil suitability. They use percolation tests, perk tests, to measure how quickly water drains through the soil.
Too slow is bad, obviously, but too fast is also bad.
Exactly. If it drains too slowly, the wastewater ponds on the surface. If it drains too fast, there isn't enough contact time for the soil microbes to effectively treat the wastewater before it reaches groundwater. So some soils just aren't suitable.
And maintenance.
Crucial. Grease traps, if used, need regular cleaning to prevent clogging the drain field. And septic tanks themselves fill up with sludge at the bottom and scum at the top.
How do you know when to clean them?
The sources actually provide tables showing typical sludge accumulation rates. The rule of thumb is to pump the tank when the sludge and scum layers occupy a certain percentage of the tank volume, usually measured from the bottom of the outlet device. Leaving it too long risks solids washing out and clogging the expensive drain field.
And those septic tank cleaners you see advertised.
Big caution from the sources there. They warn against using additives, especially harsh chemicals like acids, bases, or chlorinated hydrocarbons like solvents. They can interfere with a natural biological process in the tank, and worse, they can pass through the system and contaminate groundwater. Bad news.
Okay, what if you have a site where a standard septic system just won't work? Bad soil, high water table.
The sources discuss alternatives. Mound systems are one option. You basically build an engineered sand fill mound above the natural ground level to create a suitable treatment zone. Good for tricky sites like sloping ground or where bedrock is shallow.
Like an artificial drain field raised up.
Pretty much.
Yeah.
Another alternative mentioned is evapotranspiration or ET systems. These are designed for really tight soils where wastewater won't drain well. They rely on water evaporating from the soil surface and being taken up and transpired by plants grown on the bed.
Do they work everywhere?
They need careful design, especially considering climate. In areas without a year-round growing season, they have to be designed differently to handle flows during winter when evaporation and transpiration are low. Sometimes requires lining and storage capacity.
What about dosing tanks?
Sometimes used with conventional or alternative systems. They collect wastewater after the septic tank and then periodically discharge a measured dose to the drain field or mound. This helps distribute the wastewater more evenly over the entire absorption area, improving performance and longevity.
How are they controlled?
Usually automatic, often with a pump or an automatic siphon. But the sources flag safety concerns potential for explosive methane gas buildup in the tank, so electrical equipment needs careful placement. And like any mechanical system, they need maintenance.
Okay, moving up in scale to larger municipal wastewater treatment plants.
Right. The sources note that plants above a certain size or cost usually require design by licensed professional engineers. And disinfection is a key step here too, just like in drinking water. But now the goal is killing pathogens before discharging the treated wastewater effluent into a river or lake.
Chlorine again?
Often chlorine, yeah. Can be liquid chlorine gas, which requires significant safety precautions, or safer forms like calcium or sodium hypochlorite. UV disinfection is also becoming more common.
What kinds of treatment processes are mentioned for these larger systems?
Several types. Stabilization ponds or lagoons are mentioned. These are large, shallow ponds where natural processes, sunlight, algae, bacteria, wind, treat the wastewater over time. They can be quite effective, especially for removing BOD, biochemical oxygen demand, and pathogens, and reducing nutrients.
Can they achieve zero discharge?
In arid climates with high evaporation rates, they can sometimes be designed for zero discharge, which is a big plus. But their performance is affected by temperature, sunlight, and wind.
What about land treatment?
That involves applying treated or partially treated wastewater to land, letting the soil and plants provide further treatment. It can be a way to reuse the water and nutrients for irrigation. But the sources point out potential downsides: buildup of heavy metals in the soil or crops if the wastewater contains industrial contaminants, potential for nitrate leaching into groundwater, and issues with elements like boron, often found in detergents, which can harm some plants.
Any other older types mentioned?
Imhoff tanks are briefly mentioned, an older type of two-story tank, combining sedimentation and sludge digestion. Some design details are provided in the source material.
What about more advanced treatment, beyond standard secondary treatment?
Yeah, the sources list processes needed if you have to remove specific things like phosphorus, a major nutrient causing algae blooms, or dissolved organic compounds that resist conventional treatment, things like chemical precipitation for phosphorus or activated carbon adsorption for organics.
And the sludge that's left over after all this treatment? Biosolids. What happens to that?
Disposal is regulated by the EPA. The rules depend on the quality of the biosolids and where they're going. For landfilling, the requirements vary based on the landfill type, whether it's a monofill just for sludge or a code disposal site with regular trash. Things like liners, leachate collection systems, and even the distance to the property line matter.
Distance. Why?
Because limits for certain contaminants like arsenic, chromium, or nickel can actually be less strict if the disposal area is further away from the property boundary, providing a larger buffer zone for potential migration. It reflects a risk-based approach.
Okay, let's shift gears completely now. From wastewater to solid waste, regular old trash.
Right, and the sources emphasize a clear hierarchy for managing it. First, prevention and reduction, just making less waste in the first place.
The best option.
Always.
Yeah?
Then recovery and recycling, pulling out valuable materials, and only then, disposal of what's left.
How is it handled before collection? On-site?
Sources give examples, particularly for apartment buildings. Could be manual collection from each floor, chutes leading down to containers, different containers for trash and recycling, even sophisticated underground pneumatic systems that suck waste away.
Then it gets picked up and...
Transported, often to a transfer station first, especially in urban areas.
What's a transfer station?
It's a facility where smaller collection trucks dump their loads. The waste might be compacted and then loaded into larger vehicles, tractor trailers, or rail cars for more efficient long-distance hauling to a distant landfill or incinerator. The sources classify them by capacity and type direct load versus storage load. Haul distance really impacts the economics, influencing whether landfilling or incineration makes more sense.
Waste reduction and recycling. How effective is it?
The sources touch on the economics, noting that resource recovery often needs subsidies to be viable, but they also track the progress over time, citing recovery rates growing from maybe 7% in 1970s to around 26% by 2000 in the U.S., often driven by state or local mandates requiring communities to divert a certain percentage of waste from disposal.
What about composting? Treating the organic part of waste.
Presented as a controlled decomposition process, usually aerobic, meaning with oxygen, windrow composting is a common method described piling organic waste in long rows, windrows.
How does that work?
You need to manage the pile size, moisture, and crucially, turn the piles regularly to maintain aerobic conditions and distribute heat. The sources mention a specific EPA requirement for pathogen reduction. The pile must reach at least 55 degrees Celsius, 131 F, and be turned at least 5 times over a 15-day period.
Why those exact numbers?
That combination of heat and turning is scientifically validated to kill most harmful bacteria, viruses, and parasites that might be in the raw waste. Temperature control is key. Too cool and pathogens survive. Too hot and the beneficial microbes slow down.
Odor's a problem.
Can be, yeah. Usually linked to anaerobic conditions, lack of oxygen if the piles aren't turned enough or get too wet. So proper operation is vital. Also helps to reduce particle size beforehand, remove non-biodegradable stuff, and use clean feedstocks.
Any public health issues with composting?
The main concern mentioned is pathogen survival if the process isn't managed correctly. If temperatures don't get high enough for long enough or turning isn't adequate, there's a risk. The sources suggest that while well-run facilities minimize risk, not all might have the necessary monitoring or operational rigor. Also, potential risks for workers related to dust and bioaerosols, stressing good personal hygiene.
Okay, so what's left after reduction, recycling, composting?
Yeah.
Goes to disposal. Landfills.
Sanitary landfills, yes. The modern engineered approach. Planning is huge here. Site selection is critical considering geology, groundwater, distance from homes, requires engineering surveys, soil borings to understand the ground beneath. Modern landfills require liners, plastic membranes, compacted clay, and leachate collection systems to capture contaminated liquid that seeps through the waste, plus groundwater monitoring wells around the site to detect any leaks, and proper drainage to keep rainwater out.
How are they operated day to day?
Waste comes in, gets weighed, then spread in layers and compacted using heavy equipment. The sources mention specific types, like crawler tractors with different bucket sizes depending on the population served, or specialized steel-wheeled compactors. Compaction saves space and helps control settling. They also note equipment life and the need for good maintenance. At the end of the day, the active area is covered with soil or alternative materials to control odors, litter, and pests.
What about burning it? Incineration.
That's another disposal option. Waste is burned at high temperatures in controlled furnaces. Facilities need weigh stations too, and lots of instrumentation to monitor furnace conditions, air pollution control devices, and emissions.
Odor control.
Emissions. Odor is managed by ensuring complete combustion and having tall stacks for dispersion. Sometimes wet scrubbers are used. Particulate emissions, fly ash, are controlled using devices like electrostatic precipitators or fabric filters, baghouses, to meet strict air quality codes. The sources provide tables with typical emission guidelines.
Health concerns with incineration.
The sources state that modern, well-operated facilities with proper emission controls pose little significant risk to public health. However, public perception is often very negative, the not in my backyard syndrome.
Is there evidence of harm?
The sources say the evidence linking emissions from modern plants to specific issues like birth defects or cancer isn't conclusive, partly because pollutants disperse widely. But they do mention that high exposures to emissions from older, less controlled facilities, particularly dioxins, have been linked to conditions like chloracne and liver disorders in workers or highly exposed populations. So, while modern plants are considered much safer, the potential for long-term effects from even low-level exposure is an area needing more study.
Okay, so we've covered land and water pretty well. Let's step back and look up at the air we breathe and maybe listen to the sounds around us.
Right, air quality, what's causing the problems. The sources point fingers at major sources for key pollutants. Coal and oil-fired power plants, industrial boilers, refineries, metal smelters are big sources of sulfur oxides and nitrogen oxides.
And cars.
Motor vehicles are major sources of nitrogen oxides, carbon monoxide, and precursors to ozone.
And these pollutants feed into some really big environmental issues, don't they? Like the greenhouse effect?
Exactly. The sources explain it simply. The atmosphere traps some of the heat the Earth radiates back out towards space, kind of like a greenhouse. Certain gases are good at this.
Which ones?
Carbon dioxide, CO2, is the biggest player, responsible for roughly half the human-caused effect, according to the sources. Methane, CH4, CFCs, chlorofluorocarbons, though largely phased out now, and nitrous oxides, N2O, are also key greenhouse gases mentioned.
Any surprises there?
Well, one striking point from the sources is how potent some of these gases are compared to CO2. On a molecule-for-molecule basis, nitrous oxide is about 310 times more effective at trapping heat than CO2 over the long term. And some synthetic compounds, like HFC-23 mentioned in the sources, are incredibly potent, like 11,700 times more effective than CO2. Really highlights the impact of even small amounts of certain pollutants.
Wow. What about acid rain?
Another major issue linked to those sulfur and nitrogen oxides from burning fossil fuels. They react in the atmosphere with water, oxygen, and other chemicals to form sulfuric acid and nitric acid.
And that falls back down.
Yeah, as acid rain, snow, fog, or even dry acidic particles. It damages forests, acidifies lakes, killing fish, corrodes buildings and statues. The sources mention particularly affected areas like the northeastern U.S., eastern Canada, parts of Europe. And looking at the ratio of sulfate to nitrate in the deposition can actually give clues about whether the main source is power plants, high sulfur, or vehicles, high nitrogen oxides.
So how do we keep track of what's in the air?
Yeah.
Monitoring.
Essential. The sources describe the National Air Monitoring Network run by the EPA along with state and local agencies. It focuses on the 6 criteria pollutants for which EPA has set National Ambient Air Quality Standards, or NAQS. Particulate matter, both PM10 and the finer, more dangerous PM2.5, sulfur dioxide, SO2, nitrogen dioxide, NO2, carbon monoxide, CO, ozone, O3, and lead, PB. The sources reference the NAAQS table, showing the concentration limits set to protect public health and welfare.
How is the sampling done?
Various devices are used: high-volume samplers for particulates, continuous monitors for gases, special collectors for acid deposition. Getting a representative sample is key, meaning it accurately reflects the air quality in that area. Meteorological data, wind speed, direction, temperature is also collected because it heavily influences pollutant concentrations.
Okay, so we monitor it. How do we control it?
A combination of strategies. Air zoning, mentioned in the sources, involves classifying areas like Class 1 for pristine national parks where very little deterioration is allowed, Class 2 for moderate growth, Class 3 allowing more industrial development, though rarely used.
And regulations.
Federal standards under the Clean Air Act are paramount. This act has evolved over decades, setting emission standards for both stationary sources, like factories and power plants, and mobile sources, cars, trucks. It requires permits for major sources, mandates specific pollution control technologies sometimes, best available control technology, or BACT, and requires states to develop plans to meet the NAAQS.
Can states do more?
Yes, state and local standards must be at least as stringent as the federal ones, but they can be stricter. Other control strategies mentioned include regulating the composition of fuels, like limiting sulfur in diesel, temporary limits on industrial activity or driving during severe air pollution episodes, reviewing plans for new sources before they're built, and requiring specific control devices.
What happens to pollution once it's released? Does it just float away?
How it disperses atmospheric diffusion depends heavily on weather conditions. The sources describe how a smoke plume behaves differently, looping up and down rapidly in unstable, turbulent air, forming a steady cone shape in neutral conditions, fanning out horizontally during an inversion when vertical mixing is suppressed, or even hitting the ground fumigation when an inversion breaks up from below. Monitoring these conditions helps agencies predict when pollution levels might spike and perhaps trigger alerts or temporary control measures.
Okay, let's switch senses now. From breathing to hearing. Noise control.
Right. An often overlooked environmental issue. The sources cover the basics. Loudness is related to the sound wave's amplitude or pressure, measured using the decibel scale, dB. Frequency determines the pitch.
What's the A-weighted scale, dBA?
The dBA scale adjusts the raw sound pressure levels to better match how the human ear perceives loudness across different frequencies. Our ears aren't equally sensitive to all pitches, so dBA is generally considered more relevant for assessing noise impacts on people.
And the decibel scale is logarithmic, right? Not linear.
Crucially important point the sources make. It means a small change in dB represents a big change in sound energy. And perhaps more intuitively, the sources state that perceived loudness roughly doubles for every 10 dBA increase.
So 80 dBA sounds twice as loud as 70 dBA.
Approximately, yes.
Yeah.
And 90 dBA would sound 4 times as loud as 70 dBA. That logarithmic nature is key to understanding noise regulations and impacts.
How is noise measured?
Using sound level meters, which meet specific standards like those from ANSI, American National Standards Institute, more sophisticated sound analyzers can break down the noise into different frequency bands, like octave bands, which helps pinpoint the source of problematic noise. There are also specialized meters for impact noise or environmental monitors that can log noise levels over time.
How do we control noise once we've measured it?
2 main approaches mentioned: sound absorption and sound isolation.
Absorption first.
That's about reducing sound reflections within a space, using porous materials like fiberglass, mineral wool, acoustic tiles, heavy curtains, even carpets. They soak up sound energy, reducing echo and reverberation, making a room sound quieter.
And isolation. Blocking sound.
Right. That's about preventing sound from traveling through a barrier, like a wall or floor. This is measured by Sound Transmission Class, or STC ratings. Higher STC means better sound insulation.
Do the sources give examples?
Yeah, they provide typical STC ratings for different constructions. Like a standard gypsum board wall might be in the 30s, while a concrete block wall could be in the 40s or 50s, and a thick concrete slab even higher. Generally, transmission loss increases with the frequency of the sound, and, crucially, the mass or weight of the construction. Heavier walls block sound better.
And the other physical controls.
Yes, things like isolating vibrating machinery from the floor using resilient pads or spring mounts, putting flexible connectors in pipes or ducts, using mufflers on engines or fans, and installing air chambers or shock arresters in plumbing lines to absorb the energy from water hammer that banging noise when taps are shut off quickly.
Are there limits on how much noise is considered safe?
Yes, the sources refer to tables, often based on occupational safety regulations like those from OSHA, showing permissible noise exposure levels based on duration. For example, you might be allowed 8 hours at 90 dBA, but only 2 hours at 95 dBA, or maybe just 15 minutes at 115 dBA.
So louder means much less time is safe.
Exactly. And there are usually peak limits too, like 140 dBA for impact noise, which shouldn't be exceeded even instantaneously. It really highlights noise not just as an annoyance, but as a genuine environmental health risk requiring engineered controls.
Okay, so we've talked diseases, water, waste, air, noise, all these separate pieces. But the sources seem to argue they all need to be brought together through planning and regulation.
Absolutely. That's a central theme. Comprehensive community and regional planning is presented as the essential framework that connects all these environmental domains. They mention different approaches, traditional planning driven by community goals, versus frameworks that explicitly integrate environmental impact analysis right from the start.
What are the basic elements of planning they describe?
Pretty standard steps. Setting goals and objectives. What does the community want to achieve, including environmental quality? Doing basic studies, collecting data on population, land use, existing environmental conditions, formulating the actual plan, proposing strategies, land use maps, infrastructure projects, and then implementation. Zoning ordinances, capital budgets, regulations.
Public input important.
Stress is crucial throughout the process, making sure the plan reflects community values and concerns.
Why the emphasis on regional planning?
Because, as the sources point out, environmental problems rarely stick neatly within town or city limits. Watersheds cross boundaries, air pollution drifts, waste might be transported regionally. So regional planning is key for tackling these larger-scale issues effectively. It involves combining evaluations of water resources, water supply needs, wastewater treatment capacity, solid waste disposal options, air quality management, and land use across a wider area.
So local projects should fit a regional plan.
Ideally, yes. Even if a project is carried out locally, it should conform to the broader regional strategy to avoid conflicts and ensure sustainability.
Before anything gets built, site investigation is key.
Critically important. The sources detail the need for thorough soil studies, borings to see what's underground, percolation tests if septic systems are considered. Also looking at topography, steep slopes mean higher erosion risk. Managing surface water runoff, identifying and protecting sensitive areas like wetlands. It's all part of due diligence before development.
Need experts for that.
Definitely. The sources stress involving engineers, hydrogeologists, planners, architects, a team approach to understand the site's constraints and opportunities properly.
And environmental impact analysis, EIA, how does that fit in?
Presented as an integral part of modern planning and project design, not just an afterthought. The sources mention the NEPA National Environmental Policy Act process in the U.S., run by CEQ, Council on Environmental Quality. A key early step is scoping.
Scoping.
It's an early and open process involving the public and relevant agencies to identify the significant issues and alternatives that should be analyzed in detail in the Environmental Impact Statement, or EIS.
What goes into an EIS?
The sources give an outline. It needs to describe the proposed action and the need for it, rigorously evaluate alternatives, including a no-action alternative, and thoroughly analyze the potential environmental impacts, direct, indirect, and cumulative impacts over time and space. It also has to discuss how the project relates to existing land use plans. And, crucially, the sources emphasize basing the entire analysis on reliable data and sound scientific methods.
What about planning for new neighborhoods, subdivisions?
Mentioned as a key tool to prevent haphazard, sprawling development that can strain infrastructure and damage the environment. Comprehensive local and regional planning, Aligning zoning regulations with transportation plans and environmental protection goals can guide growth towards more sustainable patterns. Sometimes public or private land acquisition is used to assemble parcels for well-planned developments. It's all about being proactive, shaping development to fit the environment rather than constantly reacting to problems later.
Wow. Okay. We really did cover a lot of ground there. A comprehensive dive into that stack, for sure.
Yeah, from, tiny microbes making us sick to huge regional air pollution issues.
Yeah.
The systems designed to manage our environment and protect our health are incredibly complex.
It really makes you appreciate the science, the engineering, the policy that's working constantly, mostly behind the scenes.
Right. Turning on your tap, flushing the toilet, taking out the trash, even just breathing. There are layers upon layers of systems, regulations, monitoring, things you just never think about usually.
And understanding these systems, even at this level, it's not just like academic knowledge. It's about appreciating that invisible infrastructure, isn't it?
Exactly. This stuff that protects your health, the environment you live in every single day.
So maybe the next time you turn on that faucet or see the recycling truck go by or even just take a deep breath outside.
Yeah, maybe think about some of the complexity we've unpacked today. The journey that water took, where that waste is going, what shapes the quality of that air.
How does knowing a bit more about the depth and detail of these environmental health systems, how does that change the way you view your own community or maybe even your own daily routines?
That's a great question. What's an environmental puzzle or maybe a challenge in your own backyard, so to speak, that you now feel you want to understand a bit better now that you have this foundation?
Lots to think about. The deep dive definitely continues.